Alright, so let's think about this. We want to continue thinking about Cartesian coordinates. And let's recall what Cartesian coordinates are. So recall. So Cartesian coordinates are a way to describe positions in a plane very accurately using numbers. So numbers are a good way of describing positions in a line, using the number line, but if I want to describe positions in a plane, I actually need to use two number lines. So this is a clever system thought up by a philosopher called René Descartes in the 1600s, I think it was. Very long time ago. So we basically draw two number lines, one which is horizontal, one which is vertical. And the horizontal one I'm going to call the x-axis, and the vertical one I'm going to call the y-axis. And this guy is going to be the y-axis. So the basic idea is pretty simple. If I give you a point, P, well, I can drop a vertical line down from P, and it's going to give me a position on the x-axis, right? It'll give me a number, A. But similarly, I can drop a horizontal line over to the y-axis, and that's going to give me what? That's going to give me a number, B. Okay, so if I know A and B, I know the position P completely, right? So we say that this is equal to A comma B in Cartesian coordinates. So this is a way to describe a position. So sometimes we kind of abuse the notation a bit and we say P is equal to A comma B. P isn't really equal to A comma B, it's just described by A comma B when we are thinking about it in Cartesian coordinates. So this setup is called the XY plane. It's called the XY plane. So it's a plane, but we've kind of fixed coordinate system, right? We've fixed a way of describing positions. Okay, so let's think about symmetry in the XY plane. So this is a really interesting concept, one that actually you can study to very high levels, even at university, but I want to kind of just introduce to you a very basic idea of symmetry. So symmetry in the XY plane. Okay, so what are we doing? Let's take the XY plane. So let's maybe get some graph paper so that we've got a very rigid picture. Okay. So we'll have Y here, we'll have X here. Now let's choose a point. Let's choose, I don't know, let's choose a position 4, 4, let's say. So 4, 4 is here. So I'll write M is equal to 4, 4 in Cartesian coordinates. Okay, so an interesting thing we can do to the plane is to reflect in a line. So there's a line that's kind of staring us in the face, the x-axis first of all. We can reflect in the x-axis. And if I reflect in the x-axis, what happens? Well, it's like a mirror image. M would be reflected across it to that point there. Now, what's this point here? Well, I'm going to call it M prime. And what's it equal to? Well, if I read it off, it's equal to 4 minus 4. So the x-coordinate stays the same, but the y-coordinate turns into negative of the y-coordinate above. Okay, so this point, I'm going to call it something. I'm going to call it the reflection. Reflection of M in the x-axis. Well, we could do the same thing with the y-axis, couldn't we? So I could take the point 3, 6, let's say, or 2, 6 maybe. Yeah, I'll do 3, 6. Is that 3, 6? Yeah. Then I could reflect it, if I wanted, across the x-axis or across the y-axis. So what does that give? Well, that would give me a point n prime over here. And what's its coordinates? Well, now the x-coordinates change to a minus 3, and the y-coordinate, well, it's still 6. So this guy is what we would call the reflection a reflection of n in the y-axis. Okay, so let's kind of summarize this. So let's remove the paper because we don't really need it anymore. So just a little bit of terminology to describe these. This is how it's done in textbook, so I think I'll follow it too. M and M prime are said to be symmetric with respect to the x-axis. Makes sense, right? They're kind of symmetric with respect to the x-axis. And what's the kind of the general setup? Well, I might as well do this in general for you. If I had A comma B was my M prime, well, just looking at these we can see what happens. The x stays the same, but the y becomes negative. So that's what happens in coordinates. So it's kind of neat. You've got this geometric idea, this idea of reflecting across something, getting a mirror image, but it's being picked up in Cartesian coordinates a really simple way. All you're doing is changing the b to a minus b. So similarly, we have, well, exactly the same basic idea, but symmetry in the y-axis, don't we? So what is symmetric in the y-axis? Well, we would say n and n prime are symmetric with respect to y-axis. And what would the notation be again? It would be, well, if I had CD here now, that's my coordinates, then now we can see up here it's the x that switches. So this would become minus CD. So very neat, right? Again, Cartesian coordinates are giving me a simple way to understand reflections, right? At least in the x and the y-axis. Okay, so let's look at another example. Let's do the following example. Actually, no, let me get you to do an example. So do example L183 question 2. So pause the video, go to your workbook and try this question. Okay, so now that you're back, hopefully you've managed to do it. Let me introduce some graph paper so we can do this very accurately. Alright, so what have we got? Here's the setup. You should always label your axes, because sometimes you don't use x and y, you might use different letters. We'll see that when we start to think about graphs. Okay, so what have we got? We've got the point minus 3, sorry. So this is my A. First thing is B is symmetric with respect to the y-axis, so that means B is the reflection. So B is the reflection across here to this point. Okay, and this is now going to be what? Well, reflecting, it's going to be 4 minus 3. Then what is it? Well, now C is the reflection of B across the x-axis. So it's this guy up here. So this is C. And it's what position? Well, it's 4, 3 now, isn't it? Finally, D is the reflection of A with respect to x-axis. So we'll go up to here, wouldn't it? So this is D. And this is the position minus 4, 3. So we're thinking about this shape. And now it's extremely simple to do this, relatively speaking, because the perimeter we can just add everything up. So it's 8, 8, 6, 6. It's 6 plus 6 plus 8 plus 8. I think that's correct. That turns out to be what? 28 units. And the area is what? Well, it's just 6 times 8, which is 48 square units. So pretty neat. Okay. So looking at this, there's something kind of interesting we can see here. Let's notice that when I start with A and I do my reflection in the x-axis, or sorry, reflection in the y-axis, I get B. And then if I do a reflection in the b-axis, what do I end up with? So I'm doing this first and I'm doing this second. I end up with this point C. And let's notice this point C has a cool property. It's basically the reflection of A across the origin, the central point. Okay, so this is an important idea. So definition, or maybe just a picture. So if I have any point, so let's do exactly the same thing. So let's choose the position, I'll do something similar but a little bit different. Let's choose the position 3, 2 here. Let's do it in purple for the hell of it. So this is P, which is equal to 3, 2. The reflection across the origin is this. So this, the same as this, is this point P prime. And what's that equal to? P prime is -3, -2. Okay, and remember what the origin is. The origin is the central point. This is called the origin. Often written as just O for origin. I don't think I'll bother. So what do we say? Well, exactly the same as before. Exactly the same as before. P and P prime are said to be symmetric with respect to the origin. So that's some terminology for this specific situation. Let's get rid of the graph paper. And again, if we're going to do this in terms of coordinates, well, I would have D, E, X and Y. What happens? Well, we can see here, you just get the negatives. So it's going to be -D, -E. Okay, so a couple of cool facts here, right? Cool facts. The first thing is, well, we can see from our picture above, reflection in the origin is the same thing as doing a reflection in the y-axis and then the x-axis. So this is kind of a cool idea. We're kind of combining two symmetries, one reflection in the x, one reflection in the y, and getting a new symmetry, right? An origin reflection. Reflection and origin is equal to reflection in the y-axis followed by reflection in the x-axis, or vice versa. So that's kind of cool, right? We've got these two symmetries, if you want, right? These reflections. And combining them gives a new symmetry, right? This reflection in the origin. Another cool fact is the following. Well, the reflection in the origin is actually describable in another way. So let's just imagine up here. I know that we're reflecting, but we can actually do this in a slightly different way, can't we? Because we could take the point P and we could, so I'll do it with this, we could take this and we could just rotate this around by 180 degrees and it would give me this point. So reflection in the origin is actually exactly the same thing as rotating around the origin by 180 degrees. It's really cool, right? Rotation by 180 degrees. And it doesn't matter which way around you do it, clockwise or anti-clockwise. Rotation by 180 degrees around the origin. So it's kind of cool, right? What this is actually saying is the following. If I have two reflections, a reflection in the x-axis and the y-axis, if I do one and then the other, that's the same thing as a rotation. That's actually a really cool fact, right? That's something that you probably won't see again, well, honestly, until you do maybe upper division mathematics at UC Berkeley. But you see, it's a really simple idea, that's why I'm telling it to you, because it's actually really cool, and you can understand it, can't you? Because it's simple. I mean, all you're doing here is you're doing two reflections, like up here, one reflection then another. That's the same thing as reflecting across the origin, but now we've seen that's the same thing as rotating around. So very cool. Okay. So, what should we do? Well, let me kind of extend this a bit. So a bit of an extension. We can actually reflect, I mean, across any line, can't we? Reflect across any straight line. In the xy plane. So just as an example, I mean, if I had a horizontal line which isn't the xy, or isn't the x-axis, we can do exactly the same thing. So imagine I take this situation, so let's take the line which is flat here. And this position will make this, well, we know what this is. This is 0, 3. So it's kind of height 3 if you want. So if I take the point, I don't know, P is equal to 2, 1 there. It still makes sense to reflect this, right? Across the line given by this flat blue line. Okay, so I get P prime up here. That's very nice. And what's the coordinate? Well, the coordinate here is it's the same x, but now the y has changed. It goes to 5, doesn't it? So I think what we can see here is, well, the reflection across this line is not so easy to understand in Cartesian coordinates. The fact we're getting 5 there is kind of a little bit difficult. We really need to draw the picture. Here's a really interesting example, though. So instead of trying to reflect across a horizontal or vertical line, which is basically the same thing as reflecting across the x-axis or the y-axis, just moved up or down, let's take the following line. Have I gone mad? No, this looks correct to me. So take this line. Okay, so it's kind of a really nice line. It's kind of going up, I think this is kind of 45 degrees. So let me call this line L. Okay. So let's take a point P. Choose anything really. Let's choose P is 6, 2. So 1, 2, 3, 4, 5, 6. So 6, 2, that position there. And let's reflect it across this line. So if I do this, what do I get? I would get this position over here, wouldn't it? So again, you've got to be careful. This is at right angles. These are equal to each other. So what's my position? Well, up here, P prime is equal to 2, 6. So notice what's happened. The coordinates, I've just flipped them. Okay, I've just turned them around. I've put the x in the place of y and the y in place of x, and that has had some sort of geometric meaning. I think this is really cool, right? So this tells you the following. The reflection of the point, let's say P, where I'll just write it in general, it's AB in L equals, well, P prime, which is equal to B, A. So this simple thing in Cartesian coordinates of flipping the coordinates, exchanging the x with the y, actually has a geometric meaning, right? It's the same thing as reflecting in that line L. So pretty neat.